Welcome to homework.
Hello everyone, today we're doing chapter 23, problem 24, and this problem asks us that what alkyl halides are needed to prepare each of the carboxylic acids by the malonic ester synthesis. So malonic ester synthesis is essentially what you have is some sort of anhydride, and specifically you have the diethyl malonate, which is used for the malonic ester synthesis. You have that central alpha carbon here. Then what you have is those two ethyl groups on either side of the central alpha carbon. And what happens is that using some sort of base, for example, sodium ethoxide, you're going to deprotonate this alpha carbon. So you're going to make a very strong carb anion, which is a very strong nucleophile, with a lone pair of electrons and full negative charge. And then from there on, you can add some sort of alkyl halides, so some sort of Rx group, to go through SN2 nucleophilic attack, backside attack, to then add your R group now to the alpha carbon, whatever your R group is. So now you made a new carbon-carbon bond off this alpha carbon, and then you can go through some hydrolysis, acid hydrolysis, to hydrolyze these esters into carboxylic acid. So in this example, you would get something that looks like this, at which point spontaneous decarboxylation will occur to give you CO2 and your carboxylic acid. So now that we know how malonic ester synthesis works, what type of R group or what is the identity of this alkyl halide that we're going to need to generate each of these final compounds? Well, first thing you need to do is locate your alpha carbon. So here we see we have the carboxylic acid group, which is this carbon here, and then we have the oxygens. We have carbon, oxygens. This is a carboxylic acid. So then the alpha carbon is the one right adjacent to it. So it's the next carbon over. So this carbon here is going to be your alpha carbon. So that means that everything after the alpha carbon is going to be our R group. We need to add this group. So starting from this diethyl malonate, we can add, for number A, we can add our sodium ethoxide to deprotonate it, make it a strong nucleophile. Then we can add this R group. So we have 1, 2, 3, 4, 5 carbons. So 1, 2, 3, 4, 5. And that one branches off to 2. And we're adding it using an alkyl halide. So we'll add any halide. So for example, we can add bromine. So now, and this is step 2. So now when we deprotonate this to make that carb anion, we'll have nucleophilic attack on this carbon to add this R group. And then that will give us this intermediate is 1, 2, 3, 4, 5 carbons, and then we can do acid hydrolysis plus heat to have spontaneous decarboxylation, and then the other side is going to have our carboxylic acid. And we have 1, 2, 3, 4, 5. Then we get the product in A. So what about in B? So B is the same thing. So we have the carboxylic acid, and then the group right adjacent to it is going to be alpha carbon. So this is going to be the alpha carbon. So here we're adding two substituents or two R groups. We're adding this R group, and then we're also adding this upper R group. So we got to add them sequentially. So starting from our starting material, we'll add our strong base. And then let's say we'll add the top one first. We have 1, 2, 3 carbons that we're adding. So we're adding 1, 2, 3 carbons, and then we'll add a halide. This time I'll use chlorine, for example. And then we will get the monosubstituted product. 1, 2, 3. And then we'll go through an additional sequential step of deprotonating this alpha proton to make a second carbanion. So then we can add our second R group. So once again, sodium ethoxide. And then we're going to add 1, 2, 3, 4, 5 carbons. So 1, 2, 3, 4, 5. And then at 1, 2, carbon 3 is going to be a methyl group. And then at carbon 1 is going to be our halide. So I'll just say iodine for this example. So then as you see here, we're going to deprotonate this alpha proton to get a carbanion. Nucleophilic carbanions are going to do SN2 backside 180 degrees attack on this electrophile here to yield us now our di-substituted product. One, 2, 3, and then 1, 2, 3, 4, 5. And carbon 3, we have that methyl group, and then we're going to do some hydrolysis to yield the final product with aqueous water, acidic water, and heat. And we're going to form CO2, and the product of interest being this carboxylic acid alpha proton here. So 1, 2, 3. Alpha proton here. So 1, 2, 3, 4, 5. 1, 2, 3. And gets yields our product in B. And now, last but not least, using the same methodology, we can do C. So in C, we have our carboxylic acid. The carbon adjacent to it is this carbon here. So we got to add this R group, which is 2 of the same kind. So we're going to do 2 steps just like this. But now the R group, or the alkyl halide, are going to have the same identity. They're going to be 4 carbons long, each of them. So let's start off with our starting material. And we're adding sodium ethoxide to deprotonate this alpha proton to make a carbanion, which is nucleophilic, in which point we'll add 4 carbons. So 1, 2, 3, 4, and then we'll add halide. And then we're going to do this again, exact same thing, because we want to add 2 of these. So sodium ethoxide with the same reagent, and that's going to yield us our doubly substituted product. One, 2, 3, 4. 1, 2, 3, 4. And you do acid hydrolysis, and you'll get CO2 with your final product being this carboxylic acid with 2 substitutions off the alpha carbon. 1, 2, 3, 4. 1, 2, 3, 4.